Hello everyone, this is Crypto Project and I'm Yatish. This is my ID card.
Hello all, I'm Gagan Yalamuri and this is my ID card. So this is SplitSmart, our secure expense splitting system. We built it to show how real cryptographic protocols can be integrated into a simple usable web application. Even though this is a crypto project, we wanted the UX to feel like a real product. So users get real-time expense updates, analytics, and a visual ledger that can inspect themselves, and the security isn't hidden. It's visible and transparent. The backend is built with Python and Flask, and we hardened the API with HMAC integrity checks and client-side web crypto. We deployed and tested everything under attack conditions using burp suite. This is where all security starts. We use a signed Diffie-Hellman handshake, so both the client and server create fresh ephemeral keys that gives us forward secrecy. They also sign the exchange with RSA-PSS, which prevents impersonation. Then HKDF derives clean session keys for encryption. So before any data moves, we have authentication, key agreement, and secrecy. Once the session is established, every message is encrypted with the best cipher available on the device. AES-GCM when hardware acceleration is present, or ChaCha20 for lighter clients. Every expense entry is also individually signed using RSA-PSS, which gives us non-repudiation. That means no attacker can forge an expense and users can't deny submitting one.
So this is a very innovative layer that we added to the expense list which uses hash chain ledger. So each entry includes the hash of the previous hashes. So as you see in the diagram here, where it is a blockchain implementation where it stores the previous hash and the current hash and the data. And for the hashing, it uses SSA-256 along with the data and the digital signature. This is very immutable data where even if the administrator tries to attack it or modify the amount or the database or tamper the data, he cannot because it is built on a immutable blockchain ledger so that it detects any corruption immediately on the start. So to prevent some of the attack defense mechanism, we implemented some of the network attacks where it includes three model major network threats, that is eavesdropping, where this handles some of the in betweens without any ephemeral session keys if there is an eve that is collecting all the information. So for that, we are using a multi-algorithm, that is AES and a ChaCha20, to prevent this in eavesdropping attack. And next we have is a modification attack. This is mainly to prevent man in the middle of attacks. And the defense protocol that we use is uh, AEAD auth tags with some of the GCM or poly 1305 mechanism. And some of the API defenses that we use is HMAC SADA256 as headers, which verifies the request integrity and detects if there's any tampered layer with the payloads. The last thing that we are doing is identifying if there's any replay attacks. So this is done to protect the confidentiality and the correctness on the wire with monochromatic counters, and it requests for hash deduplication that tracks the hashes for every 5-minute window to reject the duplicate submissions. So that's where we are preventing against replay attacks. We are also providing defense against identity theft and integrity management. We also provide anti-spoofing techniques so that there's no impersonation. Let's say if there's a user called Alice that they're trying to, create a fake debts, this particular ledger that we built detects and prevents this from happening. And also the ledger tampering that we build prevents all this direct SQL injection and any admin modification from the server side as well. So it prevents protection against client side and as well as server side. Also it prevents against all the brute force attacks as there's a API rate limiting, so you will know when there's a limit exceeded. So we also provide some of the security coverage matrix where this summarizes everything for each attack vector, and this is like a concrete cryptographic defenses, that is all the vectors that we mentioned earlier, and that is being done with all the defense mechanism as you see here. For eavesdropping, it's AES, all the encryption algorithms, and for database tampering, it's blockchain hash chaining. All those things are protected. So before we begin into the demo, to conclude our demonstration, we provide this as a layer, as a standard primitives into a coherent architecture that we achieve to achieve the end-to-end security for suitable for any financial data, which is NIST aligned and attack resistance. So we'll quickly go into the demo right now. So before we dive into the demo, this is the architecture that we have built, which contains a web client on the browser layer as a top layer, which contains all the HTML, JavaScript interface, and then this is connected to the server that is built on Flask, which does all the routing, API routes, security, all the session management with all the session keys, and this takes an encrypted session channel through encryption algorithm like AES-256 CHA 2020 based on the length of the messages, and based on that it processes the messages in this particular ledger layer, and for storage we are using SQLite. So this is how hash by hash it is getting block by block storing the layer, storing all the messages. So this so before we dive into, we provide the authentication, safe authentication, and this is what we give as an interactive dashboard where that gives you all the analytics, all the data with all the expenses, all the entries with average expenses, with all the well designed pie chart and the line graph, with the detailed analysis of which is the biggest expense, which is the smallest expense, the recent expense. And this is where the feature that we provide for the user to add the expenses of who paid the amount and the details. As we spoke about the security features, this is the layer that we provide, and we also verify the integrity of the ledger, and this is the ledger layer that we are talking about right now. This ledger contains 10 blocks with all the chain has been well validated and been successfully verified, which contains some of the timestamp, the previous hash, the amount, and who is the payer, all those critical information. And this is how our encryption works, where we begin with the handshake level authentication that is signed by Diffie-Hellman key exchange, and then we do per entry authentication of each messages using digital signatures that uses RSA APSS, and for per message protection for that uses multiple encryption algorithms, as you mentioned, is being done with the three-layer architecture that we implemented. So these are the encryption algorithm that we used, and for blockchain ledger security, we use like a Merkle root that each blocks is included in the root hash and is very efficient for verification. And as you know, we use digital signature where expense is signed by user's private key, and we also provide a tamper detection to even nobody can modify it, and it is immutable blockchain ledger. We are mainly providing this to provide protection against eavesdropping, modifications, spoofing, replay, and tampering, and also DDoS attacks. So this is where you can see the balances, how many people who host whom. This is all the detailed structure that you can see. So I'll quickly execute one expense. Let's say I'll add an expense called Alice with amount 100, and I'll create a description, dinner, and I'll submit this. The expense is quickly being updated. Previously it was 10, now it has been 11 entries, and this will show again all the split with all the expenses. Next, we'll talk about the individual attacks, how we provide a attack techniques, prevention against all the attack techniques.
Hello, now I'll demonstrate the real time attacks. and how the application handles this. So let's start off with the modification attack. We'll log into the user. So as you can see, it is up to date, and I'll turn on the intercept. Let's say Eva paid $20 for Uber, and we'll send this to. And as a note, um, the eavesdropping attack, it will be encrypted in the real time, but for the demonstration purposes, the encryption has been turned off. So as you can see in repeater, if we try to modify the amount that has been paid, like probably 200, and send, you can see that the modification attack has been detected. And how this is happening is through the HMAC that is in place here, that's the hash. And so if we revert it back to 20 and see if the packet is accepted, as you can see, the expense has been added and it is successful. And now let's try do sending the same packet again and trying out the replay attack and see what happens. Replay attack has been detected and the packet has been rejected. So this is API level protection where the application is ensures confidentiality, integrity by by having security measures in place for modification attack, eavesdropping, and replay attack. Now I'll explain network layer securities that we have in place. So we wrote automation scripts for all the attacks that can be done at network layer, and I'll run you through each one of them. So first, let's go through eavesdropping attack. As you can see here, the attacker intercepts the message from Alice, and the attacker tries to decrypt it, and it fails, and the server successfully decrypts the message, but attacker cannot do anything with that. So what this concludes is that only parties with the session key can decrypt the message. And as for the attack 2, which is the modification attack, we can see the attacker intercepts the message, and attacker trying to modify the ciphertext by flipping bits, and the server response will be an error, and it failed to decrypt the message because the integrity check has been failed. So now attacker can't modify it, and the result would be integrity protection is successful. So attacker cannot forge valid authentication tags. And going on to spoofing attack, here imagine there are two users, Alice and Bob, and Bob tries to act as Alice and tries to send a payment, and uh, extracted payload has been Alice as the payer, but then attempts to verify through Alice's private public key, and which will throw an error because it has been signed with Bob's private key. This will ensure that the spoofing attack fails, and the result would be ensuring that the origin authentication would be successful. Moving on to replay attack, we have counters in place, and if that transaction has been repeated, the counter check will fail and the replay attack will be prevented. And going on to the last attack vector that we've protected against, which is ledger tampering. If the ledger has been tampered with by integrity, like it will check with any integrity, and if it fails, the hashes won't match, and the tampering will be failed. So it ensures that the tampering has been detected, and with that knowing, the chain will be reloaded. So that concludes our presentation, and we'd like to thank Professor for his guidance throughout this project and giving us the opportunity to work on something that brings real world cryptographic concepts into practice. We appreciate your time and feedback, Professor. Thank you.